Okay, so that's for scalar conservation laws, which is basically a single equation, a single unknown like W. The Godunov is the guy who figured out this exact solution to the Riemann's problem, and after him, people figured out other much more complicated formulas for system of conservation laws, right? When you have multiple equations. And it turns out the more equations you have, the more difficult it is, and it's at some point becomes you can only derive analytical formulas for the solution of the Riemann problem for like very specific equations. Okay, and then computationally they become also very expensive. So ultimately the solution for solving system of equations became approximate Riemann solutions. So basically, people kind of give up of solving the exact Riemann problem for system of equations, like the Euler equation for gas dynamics, and figured out approximate solutions to this Riemann problem. But this exact solution to the Riemann problem still, it's quite amazing. It can be found for a general class of equations for whatever f it is, right? As long as there is a single f and a single w. All right. Yes? For case number 5, that's this one? Yes? So for case 5, case 3 and 4, so case 3 and 4 are wi plus 1 less than wi, right? So the right value is less than the left value. Case 5 is the opposite. Case 5 takes this form. Case 5 is wi less than wi plus 1. So when you take the minimum instead of the maximum, you get the bottom. Right. Yeah. So that's the analytical solution to the Riemann problem that is found by Godunov. Yes?
What do you do with the flux also involves derivatives of W?
Okay, so what do you do if the flux involves derivative of W? Then you get a non-hyperbolic problem. So the hyperbolic problem is going to be involving so if you write down the primitive form, which is basically taking you have to use train rule to convert the derivative to f into derivative to w. Okay, then if f is algebraic function of w, then after converting it into primitive form, you get a hyperbolic equation, right? You only have first the derivative to w. If f actually involves also second derivative to w, then after you convert it into primitive form, right, which you can only allow to take derivative to w, then the primitive form would also involve second derivative to w. I mean, you can just use train rule to show that. So an equation that involves second derivative to w is going to have both, I mean, if you only have second derivative, it's a parabolic equation, right? If you have both first and second derivative, it's kind of a hybrid parabolic and hyperbolic equation. So that is, so basically what people do is usually they separate the two parts. You have a hyperbolic part, you have a parabolic part, and the hyperbolic part is going to be done with finite volume, and the parabolic part is going to be constructed separately. I mean, the parabolic part actually is usually easier to deal with in spatial discretization. But it's going to give you potentially very stiff system to solve. So time discretization can become more difficult. So if you only have parabolic terms, usually something like something like explicit solution, like OD45 actually works pretty well. If you have a strong parabolic term, right? If f depends a lot on second derivative, sometimes the equations after discretization is so stiff that you have to use implicit solution methods. There are also people who kind of do a hybrid. They use implicit solution only for the for the parabolic terms and leave the hyperbolic terms to be explicit. So anyway, the time discretization is another thing we are not going to get into in this class at all. All right. Okay, but good question. Okay, so well, let me just say a little bit about the Godunov scheme. The Godunov scheme is going to be giving a first order solution. Okay, but the first order solution is actually not Godunov's fault. It's actually, it doesn't really. Let me say this: if you are able to, if basically we have a piecewise volume averages, but it does not entitle us to say that the solution is actually a piecewise constant. We know the solution is not going to be piecewise constant, right? The direct application of Godunov scheme actually implies that we are actually approximating the solution as piecewise constant, which is actually what makes the scheme first order. Okay, to make a second order scheme, the key ingredient is not to change Godunov's solution formula. I mean, the solution formula is perfectly fine, but trying to figure out a way to not approximate the solution as piecewise constant. Okay, a very good way to do that is basically we call interface reconstruction. That is basically, okay, so we have instead of saying the left side of this interface is this, the right side of the interface is like this, we try to also compute the gradient in this cell, the gradient like this, compute the gradient like this, and maybe we can compute the gradient like this, gradient like this, gradient like this, and gradient like this. So if the solution, if the discretization is fine enough, then the reconstruction of the gradient using actually a finite difference method. Okay, basically we use finite difference method to figure out the gradient, and then use the gradient to extrapolate the solution to the interface. So we have a left extrapolation, we have a right extrapolation. They both are going to give different solutions at the interface. And then we apply Godunov scheme. Right? Instead of Wi on the left and Wi plus 1 on the right, we have a WL, which is equal to Wi plus half of delta xi times dw, well, let me write the partial w partial x at I. And w right would be equal to Wi plus 1 minus delta xi plus 1 over 2 times the derivative at I plus 1. Both derivatives are going to be computed using finite difference. Okay, we can do central difference, for example. And then we plug those into Godunov scheme, right? So then fi plus 1, I plus half is either going to be the maximum over fw, w in the space between wl and wr, if wl is greater than wr, well, just switch them, or the minimum if wr is greater than wl, right? So this is basically the way to get second order accuracy for Godunov scheme. Okay, and we are going to be discussing later how to resolve shockwaves properly over this. The key ingredients to use this to resolve shockwaves as well as smooth regions is not allowing things like this, not allowing an overshoot. So this is overshoot. So basically, whenever you have a local extrema, you have a local maximum or local minimum, then you kind of tune down this extrapolation, right? I mean, this is an extrapolation. You tune down this extrapolation to limit it, to not create new extremas, not make the maximum even higher or not make the minimum even lower. So by doing that, you get second order finite volume. All right. So that's basically what we are going to be discussing on finite volume before we get into the more advanced section of this class, when we are going to be discussing a little bit about multiple system of equations and the finite volume in more than one dimensions. Right? Any questions?
What's the minus for the right hand value?
Why is it minus on the right hand? Because the right value, well, we are going to be extrapolating. Let's say this is I plus 1. We have to extrapolate from this value to here, right? So WR is actually immediately to the right of the interface. So WL is immediately to the left of the interface, right?
So it's the delta x is actually negative because I'm going to the left. Is that one?
Oh yeah, so right, the delta x I'm saying here is the width of the volume, right? So yeah, so this is the spacing is delta xi and delta xi plus 1, right? Okay. All right, any other questions? No?